Today we are going to talk about something called the Generalized Compressibility chart and how that is used in thermodynamics. Just a brief overview. It's not a very elaborate topic that we have to work on. We basically said Z, which is compressibility factor, is equal to PV over RT. And in doing so, we said that these are both non-dimensional numbers. And we said that the temperature and our pressure, these both have to be in absolute units. So that means that they have to be in absolute pressures or absolute temperatures. That's very, very important. And I promised you that on exams, I'll give you the temperatures in relative units. So Celsius and Fahrenheit are what I'm going to give to you. I promise. And we had to find out what Z is. And if Z is equal to 1, then we can say that the gas is ideal. That we can deal with ideal gases. And that helps us tremendously. It just eliminates a lot of difficulty that we might have with problems. I not say difficulty, but just a lot of time that we might have to spend on some problems. So that is really nice. The purpose of the generalized compressibility chart is to help us find out specific volumes or temperatures or things of that nature. And we can do that already using our gas tables, but those are expansive, and so this provides us with a simpler way to find those values if we need to. Okay, and it kind of comes down to that. So what I'm going to do now is show you the generalized compressibility chart. We've seen it already on the video lecture, but just to show you again what it looks like. And so we are going to be exclusively using these three tables. It doesn't matter if we're in English units or SI. This is what's going to happen here. Figure A1 shows reduced pressures from 0 to 1. It is the one, this is the figure that we're going to use the most often. You can see compressibilities on the y-axis, reduced pressures on the x-axis, and then these black or these dark lines are going to be what the the relative temperature is, and they're listed over here. Now there are lines here called pseudo-reduced specific volume, and we'll talk about those today, but don't get confused about these numbers, as they are at a diagonal, that they are corresponding to this dashed line, and these numbers here, which are corresponding to the reduced temperature line. Okay, so we also have the next page, and we have, this is basically pressures that are reduced pressures from 0 to 10, and then if we want to go above that, from 10 to 40. I don't think there's ever a situation where we're going to use figure A3, but figure A2 is used, and in fact it'll be used on the first example problem that I have for us today. So that's the long and short of it when it comes to what we need to remember from the lecture. So we'll go ahead and get started on a problem. And we're not going to spend the whole 45 minutes here today. We have 2 example problems, and they will take us about 10 or 15 minutes apiece. So in our first problem here, we have carbon monoxide. And that is going to be CO. And we know that the temperature of the carbon monoxide is 500 degrees Rankine. We know the pressure is going to be equal to 3,500 psi. And we know the mass of this is equal to 150 pounds mass. And we want to figure out what is the volume of that carbon monoxide. That's what we want to find. And really, in everything except for today's lecture, Friday's lecture, today's in class, we're going to do all this thing where we're going to check to see if it's a real gas or an ideal gas, those kind of things, if we're close to 1 or not. Starting, this lecture is the anomaly in the class. Every other time what we're going to do is we're going to assume it's an ideal gas. We're just going to assume that when we see carbon monoxide, oh, it's ideal. And that will be what we'll go with, and that's going to be fine. But not today. So that gets kind of confusing, but it's going to be the for the rest of the semester, that's a really, really good assumption, a really, really good model. And we should, like I said in the lecture this morning, we should always go back and check to see if our model is applicable, but in most cases it's going to be. So remember when we find carbon monoxide, when we find carbon monoxide, we want to figure out here, what the reduced temperature is. So that's going to be the temperature divided by the critical temperature, and the reduced pressure is going to be equal to the pressure over the critical pressure. And we can find these critical temperatures and critical pressures if we go to our tables, and we go to table A1E. Remember, there are English tables, and I want to just make this point clear. There are English tables. There's a lot of people on the exam, too many people on the exam, that converted everything that was English into SI and tried to find SI, and it made their life terrible. Okay, so don't do that. If it's English, keep it in English. If it's SI, keep it in SI. Okay, now, in this table here, we're going to see a whole bunch of things. We're going to see chemical formula, we're going to see molecular weight, we're going to see TC, which is the critical temperature in degree Rankine, and PC, which is the critical pressure, and here they're giving it to us in atmospheres, not PSI. There's also something here called Z sub C, which is the critical pressure times the critical specific volume times, or over R times the critical temperature. This column is not needed. It looks like it maybe should be needed because it's critical compressibility factor, but you don't use that at any point in time. It will really do you no good in Thermo 1. Okay, so what I want you to do is I want you to take this information from table A1E and the information I gave you in the problem, and I want you to find the value for Z. So that's what I'm going to give you. I'm going to give you 2 minutes to work on that. Find out what your value for Z is, and then we'll come together and do this together here in a moment. Okay, that's been about 2 minutes. Let's go and see what you should have found. So the reduced temperature, we're going to go with the temperature that we're given, which is 500 degrees Rankine. And if we go to carbon monoxide, which table A1E, we can find that the critical temperature is 239 degrees Rankine. It's important that the both units in the numerator and the denominator are the same because we want a unitless value. And so we're going to calculate that, 500 divided by 239, and get a value of 2.092. For our reduced pressure, the pressure that we are given is 3,500 pounds per square inch. okay? We are given that the critical pressure is actually 34.5 atmospheres. So we have to do something about that because these units don't cancel. So the conversion here is that 1 atmosphere is 14.7 pounds force per inch squared. And now if we do this, we're going to have our units that are going to cancel, and now we can find out what our reduced pressure is. So 3,500 divided by 34.5 divided by 14.7, and we get 6.901. Okay, so those are our two values that we need, two dimensionless values. So with that, we're going to go back over here to our document camera, and we're going to pull up. We can't use figure A1 because our reduced pressure is above that one, the number 1. So we're at 6.901. We're over here very, very close to 7. And we need to find a dark line here that is about 2.09 or about 2.1. Well, we can see there's a line for 2.0 and there's a line for 2.5, but there's a lot of space in between here. So we're going to have to make a judgment call when it comes to this. So if I reach up here about 7 to where I'm going to be a little bit above this line, you know what, I see that there's an intersection right here. It looks like it probably would be on this point right here where my pointer is, where my pen is. So I'm going to read off, go all the way over here. And I'm going to say my value is approximately 1.05. Okay, 1.05 is what I'm going to use for my z value. Z is equal to 1.05. Okay. Now that I know that z is equal to 1.05, I know that z is equal to PV all over RT. I want to find volume, not specific volume. I want to find volume. So what I'm going to do is I'm going to replace that volume is equal to, or specific volume is equal to volume over mass. And so my equation is going to be equal to z is equal to PV over MRT. And if I want to, I can solve for my volume. That volume is going to be equal to Z MRT all over pressure. And doing that now, it's just me plugging in things from my equation, things that I found, to find my final answer. Okay, so Z is equal to 1.05 unitless, so don't have to worry about it. My mass was 150 pounds. My R value, now remember R, and R is a new idea here. R is going to be equal to the universal gas constant divided by the molecular weight. So let's go and, oh, people at home, I'm so sorry. Somebody here, you're in charge. You're in charge. If that screen doesn't go back, if you can't see what I'm writing on that screen, you yell at me. It's because the people at home can only see that screen over there. And I'm not good at moving away, okay? And now that I'm on that screen, I'm going to immediately turn it back on to the document camera because I want to show people something. I'm so sorry for those of you at home. I can't get this through. You think I'm smart enough. I have a PhD in mechanical engineering. I should be able to do this, shouldn't I? Shouldn't I be able to do this? God. Okay. We're going to look at, what was that? We're going to look at for R value. Okay, on the front of your conversion factors, at the very bottom down here, the universal gas constant is going to be provided for you. This is R bar, universal gas constant. And there's 1 for SI and there's 2 for English units. And we can choose. It doesn't really matter which ones we choose. It's just a matter of unit conversion. I mean, we can take this 1545 and we can convert it to this BTU one very easily if we wish to, by just dividing it by, up here, divided by 778. That's all we need to do. So it's our choice. I'm going to use the 1545, And then the next thing I have to do is find out what the molecular weight of my carbon monoxide is, and I'm going to go to table A1E for that. A1E, and I'm going to find carbon monoxide, and I'm going to find that that's equal to 28.01 pounds per pound mole. Okay, so those are two things I'm going to look at in my document camera, on my appendices. Okay, now I'm going to go back to laptop. Look at that, successfully did it one time. Gold star for Wanklin. Here we go. 1545 pounds force times feet all over pound mole degree Rankine, all divided by the molecular weight, which is 28.01 pounds mass per pounds mole. Okay, and then my temperature here is going to be given to me as 500 degrees Rankine. Divide all that by the pressure they gave me, which was 3,500 pounds force per inch squared. Now what I saw on the exam was a lot of this. That people would put things in and then leave it, and then they would just calculate. It's very, 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 very important that you not only plug things in, that you check the units. Okay, it costs some people as many as a letter grade on the first exam. So please check where we're at here. So we want to have units of volume. Okay, so here we go. Let's go through and we can cancel. Well, this pound mass is going to cancel with this pound mass. This pound mole is going to cancel with this pound mole. And this degree Rankine is going to cancel with this degree Rankine. And this pound force is going to cancel with this pound force. But now if I were to calculate it, I would have feet times inches squared, which is not good units. So I'm going to say here that I have 144 inches squared in 1 foot squared. And now with my inches squared canceled, now what I'm going to have is feet cubed. And you have to do a little bit of mental gymnastics to get that feet up there, but you can understand if I multiply the bottom by feet squared and top by feet squared, then this cancels off, and I have units of feet cubed in the numerator, which is what I want. Okay? So I'm going to go ahead and I'm going to do this calculation. I'm going to type this into my calculator. 1.05 times 150 times 1545 times 500 divided by 28.01 divided by 3,500 divided by 144, and I get 8.61 cubic feet. That's what my value is. Now let's just assume that we would have found that to be equal to we found that equal to an ideal gas. Ideal gas, what we would have done is we would have put in here for 1.05, we would have put 1. Okay, so if I divide this number, 8.61 divided by 1.05, I get 8.21 cubic feet. So this is if I assumed ideal gas. Now, let's look at the level of this number here, this 8.61, is not exact. We had to read from that figure, and we're not exactly good at reading from that figure. We said, okay, this is approximately equal to 2.09, and this is approximately equal to 6.9. We just thought, okay, that's our good point, and that's equal to a z-value of 1.05. That's a lot of us just guessing approximately where we're at in the chart. So this 8.61 is not like a hard and fast, that's guaranteed number. It's our best guess with what we're at. We used really good logic to figure it out. And then we found that the ideal gas would be 8.21. So your question when you want to go to the ideal gas model is this an acceptable amount of error for you? 0.4 cubic feet, is that an acceptable amount of error or not? And this probably is too much error. So a value of 1.05 is too high. Maybe 1.02 would be okay. You can check that. If you multiply this by 1.02, you get 8.37 cubic feet. Maybe that's an acceptable error. You have to, as an engineer, say what is acceptable. and understand how that works with your project. And when you create a model, you're going to, or look at a model, you have to go back and verify that model at the very end. I'm not going to ask you to do that in thermo. When we say use gases as an ideal, we're going to already tell you, hey, that model is going to be pretty good for our situation. But just I want you to understand, it doesn't mean that it's perfect. Some people think the ideal gas model is just the way it goes. There's many different ideal gas models that we could follow. We happen to follow this one, PV is equal to RT. That one is really simple and really easy, and it's really good for us. And it provides really decent results. But it's not perfect. Okay, it's not perfect. All right, are there any questions when it comes to this, how we use the generalized compressibility chart, how we calculated these values? All righty. Let's go to problem 2, also in English units. Now we have ethane, which has a chemical formula C2H6. And here, I've been given the specific volume is equal to 0.4 cubic feet per pound. And I've been given that the pressure is equal to 500 psi. And I want to find out what the temperature is of this ethane. So this is a small problem from what I've taught you in class. I've taught you to find out what the reduced pressure is and what the reduced temperature is, and use that information to get you on the generalized compressibility chart. Here we don't have temperature. We cannot do that. So what we're going to do here is find reduced pressure, which is pressure over the critical pressure, and then we're going to find pseudo-reduced specific volume, which is going to be the volume divided by RT critical over P critical. Now look what this is. This, if you look at this, using the ideal gas law, PV is equal to RT, and we're solving for V as RT over P. It makes sense that if we were to put critical temperature and critical pressure, we're going to get critical specific volume. That's what we're doing there. And we have values for the critical temperature and the critical pressure in table A1, so we're good to go. So that's where that pseudo-reduced specific volume is. Now, a couple years ago, I assigned a problem like this and I didn't go over the material at all. I didn't go over pseudo-reduced specific volume in class, and a whole bunch of homework assignments showed up with pseudo-reduced specific volume. And so I asked students, what is that? What is V sub R prime? What is that? And they didn't know what it was, because they copied off of a third-party source, and they had no idea what they put down. They had no idea how to use it. They couldn't explain it to me, but yet it got them the right answer. They kept saying, well, isn't the right answer, Dr. Wanklin? I said, yeah, it's completely the right answer. I said, but what is it? I don't know. I said, then you don't know anything. I mean, you don't deserve the points on this homework. And so we had to go through that rigmarole. I don't think I've done that. I think I've taken that one out of the queue of questions because I don't want to deal with that situation anymore. So anyway, that's an aside. Let's talk about this now. PR, the reduced pressure, is going to be the pressure, which is 500 psi, divided by the critical pressure for ethane. So let's briefly look here, and let's get this information. The critical pressure for ethane is going to be 48.2. And while we're here, the critical temperature is going to be 549 degree Rankine. So we'll just briefly look at this, that these are the values that we need, and then we'll switch back to the laptop so that we don't make this error again. So I have 48.2 atmospheres. I'm going to have to do my conversion here that I'm going to have in 1 atmosphere, I'm going to have 14.7 psi. And this gives me a value of 0.706. That is going to be what my reduced pressure is. For my pseudo-reduced specific volume, I was given a specific volume of 0.4 foot cubed per pound, and that's a pound mass, and I divide it by the R value for ethane, and so that's going to be 1545. I'm not going to open up the tables for those of you at home, but the molecular weight is 30.07, and this is going to be foot times pound force all over pound mass degree Rankine. Now, here's what I've done here. I have taken, this is R bar divided by the molecular weight. So R bar was on a molar basis. I divided it by the molecular weight, and immediately when I do that, when I divide anything that has a bar over it divided by the molecular weight, I immediately put it onto a mass basis. So I didn't go through that whole rigmarole where I had to convert my units here. I'm just putting it in here and putting in these new units that are going to be able for me to use. I'm going to kind of combine a step there. Okay? Now let's look at our temperature critical. Our critical temperature that we had was 549 degrees Rankine. And we're going to divide all that by the critical pressure, or I can multiply up here by the top, 48.2 atmospheres. It's the same thing, dividing in the denominators, the same thing as multiplying in the numerator. And I'm going to have to convert here and say that 14.7, that 1 atmosphere is 14.7 pounds force per inch squared. Okay, because Wanklin told me I need to check all my units, I'm going to check my units, because it seems like the guy that teaches the course, when he tells me something over and over and over again, there's something about that. Maybe he has a problem. Well, we're pretty sure he has a problem, but this problem may be something that I have too. So I don't want to, I don't want to turn out like him. I want to be better, a better engineer, have better hair. I wanted to have everything. And so I am going to check my units. Okay, so we go here. Degree Rankine goes away. Pounds mass goes away. Pounds force goes away. One of our feet goes away, so we have feet squared, and atmospheres goes away. And okay, now I have a problem here where I'm going to have, what do I have? I have too many things going away. What did I mess up here? It means I messed something up. I guess pounds. Because if I do this, I'm going to have it unitless. Is that okay? This is a unitless value. Okay, it is unitless. I want it to be unitless. I'm okay. I'm okay. And so, I thought for a moment, in my head, I'm not trying to play a game with you. I thought for a moment in my head I made a mistake, because I was thinking I need to have units here for specific volume. And then all of a sudden here in front of you, oh, yeah, okay, we're dealing with pseudo-reduced specific volume. It has no units. It can't have any units. And then calm came to my brain. All right, so inches squared, I need to know 144 inches squared is in 1 foot squared, and now that's going to cancel off here, and this is going to cancel off here, and now I'm unitless, which is what I need. I need this to be unitless. And when I type this into my calculator, 0.4 times 48.2 times 14.7 times 144 divided by 1545 divided by 549 times 30.07, I get a value of 1.447 is my pseudo-reduced specific volume. Both unitless values, both that I needed to get into my figure. And now that I have those, I'm going to go to figure A1 and see what I can do with that. So figure A1, my reduced pressure is 7.06. Okay, it's really, really close to 7. And then for my pseudo-reduced specific volume, it's going to be these dashed lines that are going up here at an angle, and I'm at 4.447 or about 4.45. So I'm going to be between these two dashed lines here. So if I do that and I go up here, I see that I'm maybe about right there. So I'm slightly above the 0.85 line. So I'm going to say my z value is 0.86. But you might say at home, that's 0.85. That's 0.85, and I would be okay with it. I would be okay with it because there's some human error inside of this. All right? Now that I know my z value, I know that z is equal to PV all over RT. I know my temperature is going to be equal to PV over Z times R. And so I can solve. My pressure was 500 pounds force per inch squared. I know I'm going to have to convert my inches squared, so I'm going to go ahead and do it. 144 inches squared is in 1 foot squared. Okay. My specific volume they gave me was 0.4 cubic feet per pound mass. My Z value was 0.86, and my R value is 1545 divided by 30.07 pounds force feet all over pound mass degree Rankine. Okay, now this one's going to have units. It has to have units of Rankine when I'm done with it. Let's see if it gives me that. Inches squared goes away. Here's 2 of my feet are going to go away. Pounds force are going to go away. The rest of my feet are going to go away. Pounds mass go away, and I have units remaining of degree Rankine, which will go into the numerator by taking this side times Rankine, this side times Rankine, and so we are okay. We have units of Rankine. We're good to go. Now, since we checked our units, we can do our calculation. 500 times 144 times 0.4 divided by 0.86 divided by 1545 times 30.07. We get a value of 651.78 degree Rankine, or 191.78 degrees Fahrenheit. And that's our temperature for the ethane in that situation using the generalized compressibility chart. These ideas, there's a lot of units coming into play. There's a lot of how do you find my R values. There's a lot of things of that nature. But it's a process that you should be able to describe to me how you do this, why you would do this. So here's what I do on tests. I don't like to give generalized compressibility questions on exams because there's too much variability in where students will find their Z value. They can be doing it perfectly correct. Some people are using straight edges and some people aren't, and they can get various different values of Z, and then when they're calculating it, they get a perfectly acceptable answer, but because of their reading of the figure, they get a little bit different one than what I get. And I don't like grading that because it's not too bad this semester because there's only 150 of you. That's a heavy weekend for me to grade. A couple semesters ago, I had 315 in thermodynamics, and that grading weekend sucked. Means totally sucked. And I grade all the exams because I think it's important that you have the professor grade because I need to know what you're doing right and doing wrong so I can work on it with you. And that's my philosophy. But anyway, that's beside the point. So I don't like to grade a whole bunch of things when somebody would maybe get 648 or 652, and that's perfectly acceptable answer. So things I would do on the exam is, for generalized compressibility, is say, here's some information, give me a step-by-step process that you would follow that tells me how you would figure out if this gas is ideal or not. And you would have to give me steps. Step 1, calculate TR. Step 2, calculate PR. Blah, blah, blah. That's what I would ask you. Or I would give you a gas and say, tell me, is this gas ideal or not? And that way, you would do the calculation. If you found a Z value that was way away from 1, you would say it's not ideal because Z is not equal to 1. And or you would find a value that is very close to 1 and say, yes, it is ideal. That's the kind of questions I would ask you. Okay? Are there any questions about this material and about the exam extra credit, which is due this evening at 11:59 p.m.? Those are 4 really good points that you can get, that they're test points to get. So I hope, usually people who turn it in get at least 2 points, possibly more. Any questions on that, on that stuff before I let you go for the day? You're all good to go? All got your exam in, all that you want? Some of you may not want extra credit. You don't believe in extra credit. It's a principle stand, and that's good. I'm okay with that as well. Okay, if that's it, then I will let you go. Have a good rest of your day. We'll see you on Wednesday.